Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the monoterpenoids. Monoterpenoid, among that only one of the example we are discussing, that is the citral. And what are the in which class it is belonging, where it is occur, how to isolate it, what are its properties, what are the uses of that citral, and then structure determination of citral. That are the point we have discussed in our previous lecture. What you are going to discuss today, let's see over here. So when we started the structure determination of citral, so first point we have learned, that is the molecular formula. Do you remember molecular formula of citral? What is the molecular formula? Anyone can tell me? Yes, it is a C10H16O. That is the molecular formula of citral. Next point we have discussed, that is a detection of unsaturation. Unsaturation, theoretically, it means that the organic compound containing carbon-carbon double bond, either double bond or triple bond, are known as unsaturated compound. And we know some of the tests from that we can detect, we can identify the presence of unsaturation by using different chemicals, and they are well-known chemical. While performing the regular experiment in the lab, organic qualitative analysis, there we have used those, and their mechanism, how the reaction takes place, how the mechanism, the detailed mechanism of these reactions we have learned in our previous semester, in semester number 3 also. And from that, but particularly as far as the citral is concerned, in a citral there is 2 carbon-carbon double bond found in the citral. How? Because how will you prove the presence of 2 double bond in the citral? We have suppose take or consider the citral molecular formula. We know that C10H16O, and then we treated this citral with the bromination Br2 in presence of CCl4 gives tetrabromo derivatives in one way, whereas the same citral, same substituent we are treating with the H2 in presence of catalyst, maybe as a platinum, palladium or nickel. The product obtained, analyzed, is the tetrahydro derivative, and from these 2 reactions, bromination and hydrogenation, clearly indicate or suggest the presence of 2 carbon-carbon double bond in a citral. And next point we have learned, the acyclic or the open chain structure of the citral. The formula for parent saturated hydrocarbon of citral becomes C10H22, which correspond to a general formula CnH2n+2, suggesting that citral is a acyclic open chain terpenoid. So up till now we have discussed in details now the nature of oxygen. As we know that if oxygen atom is involved in the molecular formula, it is associated with different functional group such as hydroxyl group or alcoholic OH group, carbonyl group, maybe aldehydic or ketonic, then carboxylic group, then oxo group, then acetyl group. These are the various form of that oxygen nature if it is present, and as we know that a citral containing as a oxygen atom, and therefore it is necessary to find out in which form it is present in the citral, that we are learning over here. Now here the nature of oxygen in the first point we are discussing, we are learning. Citral forms an oxime with hydroxylamine and bisulfite addition product with saturated NaHSO3 sodium bisulfite, and therefore citral contain either aldehyde or ketonic group. As we know that when that citral, assume that citral when it is treated with citral, as we know that it has molecular formula C10H16O. This is, as we know that it is a citral, right? And when this citral treated with hydroxylamine, NaOH, this is the ammonia derivative. When it is reacted with this hydroxylamine, it forms as a oxime derivative, suggesting that there is a carbonyl group is present, and that carbonyl group, it is what we can call it as this carbonyl group, whether it is aldehyde or the ketonic group, that therefore citral contain either aldehyde or the ketonic group. That's the confirmation we have got over here, right? When we treated this citral with hydroxylamine derivative, it produced the oxime derivative, whereas the same citral we treated with sodium bisulfite gives the addition product of the bisulfite addition product. Both prove the presence of, both gives the proof of presence of, or both are suggesting the presence of aldehyde or ketonic group in a citral. That's the first point we have seen over here. Now let us move on to the next point. The next point will be B. Citral on reduction with sodium amalgam in dilute acid forms a primary alcohol, geraniol, and citral on mild oxidation with moist Ag2O gives geranic acid without loss of carbon atom. Now these are the two reactions, what they suggest, what they indicate, or what they are going to prove the nature of carbonyl group, whether it is a aldehydic or ketonic. That B point we are learning over here. Now we know that the general formula of citral C10H16O. This is the general molecular formula of citral. Now we are trying to prove, suppose let us assume here this citral has this citral containing the aldehyde group. When it is treated with reducing reagent like sodium amalgam in presence of dilute HCl, that is a Clemmensen reduction, which is a very good reducing reagent which reduce the carbonyl group. It may be as a aldehydic or the ketonic, and that forms as a geranyl. That form as a geranyl, or what you can write here, the molecular formula, carbon remains as it is, C10, H, only 2 hydrogen atom added. So you add here 16 plus 2 becomes as 18, and oxygen becomes as this one. The same reagent, when you treat with that aldehyde, we are assuming here citral containing as a aldehyde. When it contains as a aldehyde group, it must convert into as a CH2OH. This is a primary alcohol, right? Alcohol, and this is known as a geranyl. Geranyl clearly indicate that there is a means aldehyde group is converted into as alcohol, geranyl. The same citral, the same substrate, when it is treated with moist, that is a mild oxidizing reagent, moist Ag2O, silver oxide, it is a mild oxidizing reagent. What it will do? It will convert the aldehyde group into as a carboxylic group, and therefore you are going to get over here moist Ag2O. So here you are going to get C10, H16 and O2. One oxygen atom is added over here, and the name of this compound is a geranic acid, which we obtain here, and here what you are going to get are COOH, which is a carboxylic group. This is the general reaction takes place when any aldehyde treated with mild oxidizing reagent, they produce the carboxylic acid. This is a carboxylic acid, that is a characteristic of that aldehyde group, and therefore this suggests that the citral containing as aldehyde group, understood this? This citral on mild oxidation with moist Ag2O gives geranic acid without loss of carbon atom, and both these reaction confirm. Both these reaction means these above reaction, one is a reduction reaction, another one is a oxidation reaction. Both these reaction confirm the presence of an aldehyde group is aldehyde group in a citral. So in question, in exam, the question may appear such as, how will you prove the presence of aldehyde group in a citral? At that moment, you must remember this, write down the general formula of citral, then treat with sodium amalgam, that gives the geranyl, means reduction takes place, and another reaction, the same citral, same substrate, when you treat with moist Ag2O, which is a mild oxidizing reagent, which will convert aldehyde group into as a carboxylic group, where in a citral you are getting as a geranoic acid, it clearly, and both these reactions confirm the presence of aldehyde group present in the citral. Got it? So this is the in this way you have to write the answers of question in the exam. Okay, now let's move on to the next point, position of the aldehyde group. Right now on these two, both reaction indicate the presence of aldehyde group in the citral, no doubt about it. Now we are going to find out where it is actually present in the citral, that we are trying to find out over here. Let's see next one. What is that? We are that fifth point we are discussing over here. What is that? Position of aldehyde group. Now is a position of aldehyde group. That is the point we have discussing. We confirm that means both reaction confirm the presence of aldehyde group in the citral, no doubt. Now we are trying to find out where it is present. What is the position of aldehyde group in the citral? Because we are trying to find out the carbon framework or carbon skeleton of that citral molecule. So for that, position of aldehyde group. Number one test we are trying to perform here. What is that? The UV means ultraviolet rays. The UV ultraviolet spectrum. Now spectrum, do you know? Spectra and the spectrum. Spectra means single, spectrum is different. That is a plural form of that. Singular and the plural form in English you might be knowing that single, plural and the singular and the plural. So that is the form of that. Spectrum means there are different the spectrum. By analyzing the spectrum which from spectroscopy, the UV spectrum of citral shows an intense peak at lambda max 238 nanometer, which is a characteristic of conjugated aldehyde. Look at here, the UV spectrum of citral. UV spectrum of citral shows an intense peak. Peak we can call it as a band or signal. Or you can call it as a signal, band or peak. These are the synonym word for this particular word. That intense peak at lambda max 238 nanometer, and as we know that 1 nanometer is equal to 10 raised to minus 9 meter or 10 raised to minus 7 centimeter. That is the general relationships we know that, which is a characteristic of conjugated aldehyde, which is a characteristic of conjugated aldehyde. Conjugated aldehyde. Do you know conjugation or isolation? Conjugated means what? They should be alternative. So such type of the aldehyde. Here is a carbon-carbon double bond, and then these are here. You can write as a Z. Carbon-carbon double bond, single bond, and this double bond. So that type of the system are known as conjugated system. An isolated system, suppose you have a double bond over here and then you have a aldehyde over here. Here is a Z. So even though there is a carbon-carbon double bond as well as, but they are separated by two single bond, and therefore it is fall in the isolated double bond. This is called as a isolated double bond. This is called as a conjugated double bonds. Conjugated, and when the conjugation is increases, the stability of that molecule increases. Hence, the number of resonance effect, canonical form also goes on increasing. Stability of that molecule also goes on increasing. So that is the reason why it is increases as far as the conjugation goes on increasing. So that is the reason. So here the UV spectrum of citral shows an intense peak at lambda max 238 nanometer, which is a characteristic of conjugated aldehyde. Ultraviolet spectrum, that what do you mean by the ultraviolet spectroscopy? As I already because in this semester we are going to learn the spectroscopy, different spectroscopy we are going to learn. These are the modern method for elucidation or for structure determination of that organic compound. And UV spectroscopy, generally as these are the spectroscopic method. Let us see the definition of the spectroscopy means what? The interaction of electromagnetic radiation with matter is known as a spectroscopy, because electromagnetic radiation, interaction of electromagnetic radiation with matter is known as a spectroscopy. That is the simplest definition of the spectroscopy. And whatever ultraviolet rays, infrared ray or IR, infrared rays, microwaves, whatever waves, they are nothing but as a electromagnetic radiation when they fall on the matter, or what we can call it as on a molecule, particularly the functional group which can absorb that electromagnetic radiation, and responses are given by that functional group or that molecule, and that responses are recorded in the form of spectrum, and by studying that spectrum, and the chemist come to know that what type of the functional group or what type of the compound they exhibit or they can show. So that is called as a spectroscopy. While the spectroscopic method, these are the spectroscopic method we will learn while studying that spectroscopic method. So in this semester only we are going to learn the spectroscopic method such as ultraviolet ray, infrared spectroscopy, NMR spectroscopy, or we can call it as a PMR spectroscopy, and these are the spectroscopy. By using this we are trying to find out the correct structure of the compound. Ultraviolet spectroscopy, it is a separate method. It gives some of the important information about the structure of the unknown compound. Now, what kind of the information it provides to the chemist? It provides the information related to as a carbon-carbon double bond, whether it is in a conjugated form or in a isolated form, that type of the information. Because for this spectroscopy, the sample, few milligram of the sample is required. There are spectrophotometer, UV spectrophotometer or visible spectrophotometer. When we are providing the in a suitable solvent, within 3 to 5 minutes they give us the spectrum, and by analyzing that spectrum, chemists can analyze those spectra similar to as a doctor by looking our what we can call it as a images on that monitor, whether if there is some diseases are there. By looking that ACG, that type of the spectra, they come to know immediately what kind of the diseases that person has. Similarly, chemists also, by analyzing that spectrum, they can easily understood what type of the functional group they exhibit or they shows. So this is one of the characteristics when the peak observed at 238 nanometer lambda max, according to as a Woodward and Fisher projection. How to calculate that we will see during that UV spectroscopy. But here just remember this is the lambda max peak or the signal or the band appear around 238, which is a characteristic of the conjugated aldehyde. And conjugation system, first you know that the system which is placed double bond separated by the single bond only, that type of the system is known as a conjugated system. If they more than two single bonds are present in between that double bond, then they are they are belonging to as a isolated system. So that is the thing you have to remember over here. Then B point here we are going to see. Let us see the another point, B point here. What is that B point? So here citralon hydrolysis with aqueous K2CO3, that is a potassium carbonate solution under high pressure, gives aldehyde and a ketone, aldehyde and the ketone, that is methyl heptanone 6-methyl hept 5-en 2-ONE. So that type of the reaction is occur over there. Let us see the position of that aldehyde. So we know that in the first point we have seen the lambda max appear around 238, which is a characteristic. Aldehyde group is present over there, but it is present in the conjugation with the double bond. Now the B point we are discussing here. What is that? Citralon reduction, the citralon hydrolysis with aqueous K2CO3 solution under high pressure gives aldehyde and the ketone, that is methyl heptanone. Let us assume here, what is assumption we are assuming here? Let us see here the aldehyde group. We can here double bond, as we know that aldehyde group present in the conjugation, that we are assuming. We don't know the rest of the structure. What we know right now, we know that aldehyde group which is present in the conjugation. That's why that part I have shown over here. And when this part boiled or treated with K2CO3, that is a potassium carbonate which is a base, and after that what you are going to get? You are going to get over here the carbon atom, then this hydrogen atom get replaced by here the OH, then C, then CHO. Aldehyde group remains as it is now, not this one. So here 1, 2, 3, no, this one. Let me draw this properly. 1, 2, 3, 4, 5. Here is no hydrogen atom because carbon never show the 5 bond, only 4 bonds are there, and therefore here we can put as one of the hydrogen atom. Then this hydrogen at this position OH is come, hydrogen atom and the CHO. This type of the species is obtained over there, and this species further treated with water, just work up, the bond is going to break from here in presence of ice. So you are going to get here this one C double bond O ketone, as well as what you are going to get here, this one hydrogen atom here, another hydrogen atom, and this is a CHO. This is acetaldehyde which we got here, acetaldehyde. Or before that we can write this after breaking this one. So we get here OH and this OH. This is a Sem diol we are getting, right? And Sem diol, which is a very unstable, further it is treated with H2O, it is get converted into as a carbonyl group like this. This is a ketone we got over here, that is a ketone, and this is nothing but the compound which we got over here. This type of the compound we will get oxygen atom here, and this is nothing but as a heptanone, right? This compound is known as a methyl heptanone. This is known as a methyl heptanone. This is the name of this compound which we got after doing this. So it means that methyl heptanone we have got over here. So how will you prove the presence of conjugated double bond in the citral? So there are the two methods. By using two methods, you can easily prove or you can confirm that the aldehyde group is present in the conjugation form, and both reaction prove that citral is a conjugated aldehyde, that is alpha beta unsaturated aldehyde. So this is the proof for the what we can call it as a carbon carbon double bond. So I think this is the way of explaining this point, nature of the oxygen atom. We have seen the position of the aldehyde, where that aldehyde group is present, and then in the next lecture we are going to learn where the carbon skeleton is present in the citral, that type of the thing, and rest of the point we will discuss in the next lecture. Let us stop today's lecture over here. Have a nice day. Thank you.